So our last section here in Chapter 8, we're going to be solving more complex trig equations. Trig equations we've had before were pretty straightforward, easy to get to a sine inverse, cosine inverse, tan inverse stage and you answer the question. And now the equations are going to appear a little more complicated and we're going to have to do some algebraic manipulation before we can go to our inverse trig tools to answer the question. So suppose I want to solve 2 sine theta minus cosecant theta equals 1 for theta between 0 and 2 pi. Now, if I've got a calculator, I could put the left side into y1, the right side into y2, set my window from 0 to 2 pi, and do a second calc intersect and answer the question. True, but suppose I don't have a calculator and I want to solve this trig equation as is. Well, one good strategy we've had for simplifying trig expressions and proving identities is to convert everything into sines and or cosines and see what happens. So the first thing I'm going to do is convert that cosecant expression into a 1 over sine. And I note at this point, again, there's some restrictions. If I'm looking at this equation, clearly sine theta can't equal 0. So I know theta can't be any multiple of pi, because then I would get a 0 in the denominator here and we'd be undefined. So I note, and again it might not come into play, but I certainly know that theta can't be any n pi values at this point. So now I look and say, well, let me clear denominators here. Let me go ahead and multiply both sides by sine theta, because then that's going to clear a denominator. It also, as you can see, it's going to give me a quadratic expression when I multiply both sides by sine theta. So we get 2 sine squared theta minus 1 equals sine theta. And then with the quadratics expression, we know we've got a variable squared, we have a variable to the first, and we have a constant, so we have a quadratic expression. And to solve a quadratic, we set one side equal to 0 and look to factor. So I'm looking at 2 sine squared theta minus sine theta minus 1 equals 0. And at that point, then I can say, well, let me factor this. 2 sine theta sine theta equals 0. My only factors of 1 are 1 and 1. And I need to get a negative sine theta out, so that's going to be negative. That's going to be positive. So then I get 2 sine theta plus 1 equals 0, or sine theta minus 1 equals 0. And I solve, and I get sine theta equals negative 1/2, or sine theta equals 1. Let's see, where does, between 0 and 2 pi, where does the sine equal negative 1/2? Well, that's going to be at 7 pi over 6, or 11 pi over 6. And where does sine theta equal 1? At pi over 2. So I wind up with my 3 solutions here. Okay, so here's another example. Still solving from 0 to 2 pi, and I've got 6 sine squared theta equals 7 minus 5 cosine theta. And the one problem we notice is we've got a sine squared, and just a cosine. And generally, for looking at these equations where quadratics can come into play, obviously you want your quadratic term in sine and a linear term in sine. So the question is, how can I get this all in terms of sine or cosine? And the easiest way would be to consider sine squared from our Pythagorean identity. Sine squared plus cosine squared equals 1. So if I want to replace sine squared with what it's equal to with cosine squared, I can get the whole equation in terms of cosine squared. So the first thing I'm going to do is 6, 1 minus cosine squared theta equals 7 minus 5 cosine theta. Expand 6 minus 6 cosine squared theta equals 7 minus 5 cosine theta, and then get one side set equal to 0 and get your quadratic as your first term. So I'm looking then at 0 equals 6 cosine squared theta, moving that over to the right. If I move the 6 over, that's going to give me a plus 1, and then I'm looking at a minus 5 cosine theta. So now I've got a quadratic expression in theta, and then I can go ahead and factor. So 0 equals, and I've got choices here. What am I going to do? A 6 cosine and a 1 cosine, or a 2 cosine and a 3 cosine? Well, I'm just going to have to try it out. Let's do a 2 cosine theta and a 3 cosine theta. And then my only factors of 1 are 1 and 1. I know I'm supposed to get a minus, so, or a plus at the end, so it's got to be minus minus. So negative 3, negative 2 is negative 5, negative 5 cosine theta, that looks good. 2 times 3 is 6, 6 cosine squared theta, that all looks good. So then therefore 2 cosine theta equals 1, or 3 cosine theta equals 1. Cosine theta equals 1/2, or cosine theta equals 1/3. So, going from 0 to 2 pi, where's my cosine? Equal to 1/2. That's pretty easy. That's going to be at pi over 3, or at 5 pi over 3. That's easy. And now over here I'm looking for cosine theta equals 1/3. Well, I know I'm going to get here, and I know I'm going to get here. So I do my cosine inverse of 1/3, which is going to give me a reference angle. That's about equal to, and let's see, that's 1.23 for my reference angle. So therefore my other angle, if I'm going to go all the way around and use that reference angle, it would be 2 pi minus 1.23, which is about 5.05. So I've got four answers, about 1.23 radians, 5.05 radians, or pi over 3 and 5 pi over 3. So looking at this one, your one immediate reaction might be to go ahead and divide both sides by sine x, because if you do that, then you get secant x equals 2, and that looks a lot simpler. The problem with doing that, and you can do that, that's permissible, but what happens if sine x equals 0? 0 times anything is 0, 0 times 2 is 0, so where sine x equals 0 is going to give you a solution. And you remember back from working with these problems algebraically, when rather than having a sine x, if it was just an x or a t or something, better strategy might have been to set one side equal to 0, and then go ahead and factor out on that one side your sine x. So sine x, then your secant x minus 2 equals 0. And then you've got two factors, sine x times secant x minus 2 equals 0. So you go ahead and set each factor equal to 0. Sine x equals 0, or secant x minus 2 equals 0. And again, I agree. If you see that sine x equals 0 is going to give you a solution up here, you can divide both sides by sine x, making sure you find the solutions where sine x equals 0 that are answers, and then you could go on and deal with the secant x equals 2. So where does sine x equals 0 from 0 to 2 pi? And that's going to be easy. That is going to be at 0 or at pi. Where does secant equal negative 2? Well, secant x equals 2. That would mean cosine x equals 1/2. where does cosine x equal 1/2? That would be at pi over 3 and 5 pi over 3. So I've got my 4 solutions. So we're up to a cubic here, and this kind of should look familiar to you back from Algebra 1 and Algebra 2 as something like a 2x cubed minus x squared minus 2x plus 1 equals 0. And you might remember we looked at factoring by grouping. We saw a 2 and a 1 and a 2 and a 1 here. So we looked at factoring this by grouping. We pulled out an x squared out of these two terms, and we made sure we put parentheses and had our minus here. So in other words, this was looking at pulling out an x squared. That would be a 2x minus 1 minus, and if I'm going to put that in parentheses, it would be a 2x minus 1 equals 0. And then I look to factor out a 2x minus 1 out of each term here, leaving me an x squared minus 1. So that's what we did back in the Algebra 1, Algebra 2 world. And we're going to do the exact same thing now with our trig expression. So let's see if we can pull ourselves back here. Come on. So again, where were we here? We had a 2 sine squared x, 2 sine cubed x minus sine squared x up there. I'm going to pull out a sine squared x. And that's going to leave me a 2 sine x minus 1 minus, pulling out a minus sign, 2 sine x minus 1 equals 0. Then what can I factor out of each of these two terms? A 2 sine x minus 1. So that's going to leave me a 2 sine x minus 1, leaving me a sine squared x minus 1 placement holder. And then I go ahead and set each of those factors equal to 0 because I have now a product 2 sine x minus 1 times sine squared x minus 1 equals 0. How can two numbers multiply and get 0? Either one is 0 or the other 0. So 2 sine x minus 1 equals 0, or sine squared x minus 1 equals 0, in which case I get sine x equals 1/2, or sine x equals plus or minus 1. And then I can actually answer this question pretty simply. Where does the sine x equal 1/2? That will be at 5 pi over 6, or pi over 6. And where does the sine x equal plus or minus 1? Between 0 and 2 pi, at pi over 2, or at negative pi over 2. So I get 4 solutions. So this one here is looking this problem here is looking innocuously simple. I've got just a sine and cosine, and what can I do to solve this? And the problem is that if that 1 minus weren't there, certainly I could get a tan x equals 3, but there's really nothing, I can't do anything. Now if I had a y1 for 1 minus sine x, a y2 for 3 cosine x, sure, I could do it on my graphing calculator, do second calc intersect of those points. But to solve for 0 to 2 pi here, it looks like I'm going to have to do some different type of work. And here's what we're going to do. We're going to use our Pythagorean identity, sine squared plus cosine squared equals 1, and we're going to solve for either sine or cosine, getting a radical expression involved. So I'm going to do this here for cosine. I could do it with sine, but I'm going to do it with cosine. So if I rewrite here now, I get 1 minus sine x equals 3 times plus or minus the square root of 1 minus sine squared x. Go ahead and square both sides now to eliminate the square root. So I'll get 1 minus 2 sine x plus sine squared x equals 9 times, parentheses, 1 minus sine squared x. And not quite sure why I lose my huge picture like that every time, but let's pull her back up. And at that point then I can go ahead and say, all right, let's combine like terms. Expand the right side and combine like terms. So 1 minus 2 sine x plus sine squared x equals 9 minus 9 sine squared x. Get everything on one side, because now note I've got a quadratic expression, a sine squared stuff, sine stuff, and constants. So 9, be looking at 10 sine squared x, that takes care of those two, minus 2 sine x, takes care of that one, bring the 9 over, minus 8 equals 0. I could factor out a 2, so I get 5 sine squared x minus sine x minus 4 equals 0. And let's see if this is going to factor. Equals 0. So I'm looking at a 5 sine x and a sine x. And my factors of 4 are 4 and 1, or 2 and 2, and I've got to make sure I get a negative sine x out of it. So let's see, if I were to do a 4 and a 1, they both have to be, one's a minus, one's a plus. So let's see, I want a minus sine x, so plus 4 minus 5 is going to be minus 1. 4 times negative 1, negative 4. Yep, that looks good. So, continuing along then, I then would have 5 sine x plus 4 equals 0, or sine x minus 1 equals 0. Sine x equals 1. So I'm looking at pi over 2 as an answer. Over here I'd be looking at the sine inverse of negative 4/5 as a reference angle, equals x, and I know then my sine is negative, so I know I'm going to be looking at something over here or something over here. So I'm going to have a third and fourth quadrant angle, and I would use my sine inverse tool. So sine inverse, I will lose my sine inverse of negative 4/5 if I want, and that's going to give me negative 0.92, and so that means my reference angle then is 0.92, and to get that, those two angles, one of them is going to be over here, one of them is going to be over here. So with that 0.92, it looks like I'm looking at a pi plus 0.92 and a 2 pi minus 0.92, and those values turn out to be. So the only issue here is, thinking back in Algebra 2, we've gotten some answers, and we do want to go back and consider something. Up here, we squared both sides of our equation, and when you square both sides of an equation, you might remember from Algebra 2, you got to be careful and check for extraneous solutions. So you want to actually go back in and make sure your answers are going to make sense. So if I put pi over 2 in, back up here for my original equation up here, 1 minus sine x equals 3 cosine x. If I put pi over 2 in, sine of pi over 2 is 1, 1 minus 1 is 0, 3 times the cosine of pi over 2 is 0. So pi over 2 checks out. It certainly looks good. I then got two other solutions down here. I got the 4.06 and the 5.36. Let's remember that The 4.06 was a third quadrant angle, and the 5.36 was a fourth quadrant angle. So let's go back up here again and look at our original equation and see about a third and fourth quadrant angle. Third quadrant angle, the sine is negative and the cosine is also negative. So if I'm looking at our equation 1 minus sine x equals 3 cosine x, and I'm in the third quadrant, sine's going to be negative. 1 minus a minus number, that's a positive number. The cosine for that third quadrant angle is going to be negative. Can a negative number equal a positive number? And the answer clearly is no. So that would mean that this one answer over here that we got is an extraneous solution. It doesn't work. How about a fourth quadrant angle up here? Let's take a look at our fourth quadrant angle. Up in our original equation, fourth quadrant angle, sine is going to be negative, so 1 minus a minus number is going to be a positive number. Cosine in the fourth quadrant is going to be positive. Can a positive equal a positive? Yes, indeed. So, indeed, for our fourth quadrant angle, that looks good. So, our solutions then, we get two solutions. We get the 5.36 and we get the pi over 2. So we do get our two solutions. Pi over 2 and our 5.36.